Hey everybody, this is Alex Merced from alexmercedcoder.com. And what I want to do today is just kind of if you've seen some of my previous videos on computer science, and you can find the computer science playlist over there at devnursery.com. I've talked about sort of like different data structures, and a lot of times if you start learning programming from a higher level language, this is like JavaScript, Python, Ruby, it's hard to kind of appreciate, why do I need to know what these data structures are? The reason being is that those languages kind of already have those data structures built into them. Okay, you know, a lot of the reasons, like, it's more appreciable if you take a look at a language like C, where just none of that stuff exists. Okay, C, you're really dealing with just a few very slight abstractions over the computer's memory. So in that case, you want to create more usable ways of working with the computer, you have to create those structures yourself. I mean, in C, you don't even have classes. But so what I'm going to do is just kind of talk a little bit about what's going on in the computer's memory, so you can kind of appreciate why different data structures exist. So first I'm going to talk about, so imagine that each of these squares is essentially a block of memory. I'm not going to worry about whether it's a byte or 4 bytes or anything like that. Just think of it as it's a block of memory. Okay, and they all have a physical space. Like, see, like this, like for this memory to go then point to this block of memory here, they are physically further away from each other, which means it's going to physically take longer and take more time for me to use whatever's here and then immediately use whatever's in here. Okay, so there's actually a physical component to managing your memory. Okay, so a pure array, so this is not like necessarily arrays in JavaScript, Python, or Ruby, which are, those arrays are implemented, meaning they create the illusion of an array, but they are actually more complex data structures underneath. If you're using C, an array is literally just a block of memory. Okay, so let's say I wanted to create an array with the numbers 1, 2, 3, 4, 5. Okay, then essentially I'm taking up 6 blocks of memory, because this other block is going to maybe have something like this that marks like it's the end of the array. Okay, so then I am taking up this space. We'll use, okay, so there's my array. It takes up physical space in memory, and there's actual like memory allocated that's literally right next to each other for that array. So I can't really expand this array, because already this memory's already been allocated. Like, this is a thing that's inside the computer's memory that said, okay, here we have this memory for this thing. So if I wanted to create if I wanted to like add data to this array, I can't add data to it. I'd have to create a new array. So I'd have to create some sort of way to generate a new array. So let's say I want to push the number 6 into this array. I'd have to take in some other array, and again, all this memory may have been used already. So again, as your computer runs, it's allocating memory. So maybe by the time we make a new array, we're here. So I need 1, 2, 3, 4, 5, 6 spots plus 1 for the end. Okay, so this is going to be our new array and then I have to copy over this. So using some sort of programming stuff, I have to kind of loop over this array and say, okay, well, the first thing in this array equals the first thing in that array, then the first thing in that array, that thing in that array, that in that array, that in that array, then inject my new number, and then again mark the end of the array in memory. So now I'm taking up 7 spots. Okay, and you can see like there's this physical, I have to keep going back here to get the information, then put it in here, then go back to the next one. There's this sort of what's called traversal. I'm moving around sort of all these spots in memory. Okay, and that's kind of how an array works. Okay, a true actual like what's going on under the hood with an array. So the problem is, and then after I create my new array, then I have to go back and then free up this memory. Okay, then I have to go back, free this up. So in C, I'd actually have to go back up, free it up, so that way this memory is no longer being used, and it can be available for something else. Okay, that's a lot. If you saw my videos on C, you'll realize like that's a lot more coding than one would care to bargain for. But again, you would do that because you want that more granular control in your programming, because you're building like an operating system, or you're building a compiler for a new language, where you really kind of want that manual memory control. And again, in higher level languages like Python, Ruby, and JavaScript, they're going to implement an array in a different way. It's not actually an array. I'll tell you how they do it in JavaScript in a little bit. Okay, so another type of structure you might have heard of is a linked list. So let me first just free up my memory. There we go. So in a linked list, what you do is you can have an expanding list of related data without having to create a whole new structure. So basically, but the thing is, here's what happens. Okay, here I'll put like a dash, meaning like null. Okay, and then here I'll have my data. So here we'll have the number 1, and then here I'm going to have a pointer that points to wherever the next item is. Okay, that's so for one piece of information, I'm taking up 3 blocks of memory. Okay, and then we'll color that as this. And then say later on, I want to add something. I want to add something to this linked list. And if you hear my bird in the background, I do have a cockatiel who's right now flying around and chirping. Okay, but then what would happen is that at that point, I'd say, hey, I want a new node. It would create a new node over here. So we'll just color that again. And then this would have a pointer to the previous node, meaning this actually literally has the address of where this node is located. Then here's my second piece of data. And then there's another piece of data with a pointer saying where's the address of wherever the next, that's going to hold the address of the next piece of data. So I can start from the first item and see there's no pointer to an item before it. So in that case, this is the beginning of the linked list. I can see here's the information, and then here's the thing that points to the next item. Following that pointer, I can then find the location in memory where the next item looks. I can see there's the item of data, and then here's a pointer to the next one. Okay, and then, you know, this kind of goes forth, and I can keep adding. Let's fill that with that. And then that, again, will have a pointer to the previous node. There's my next piece of data, and then the next pointer. So essentially the way this works, that this points to here, then this points to here, and I have to traverse back and forth between this linked list. Okay? So that's kind of how a linked list works. And you can see here, while this allows me to have a data structure that's more flexible, I can remove and add nodes. They all connect to each other, so I can only really remove the last node. And in order for me to, let's say right now I have like, my linked list is pointing at the first item, I have to then go through the second item before I can get to the third item. So traversing all these different nodes is a little bit more processy, meaning it takes a little bit more time, not because it doesn't take us, you're taking up more space memory wise, because again, I'm taking up all these space for the pointers. And on top of it, there's a lot more logic and processes that the computer has to go through to go from, say, hey, oh, here's the first item, let me go find the next pointer, here's this thing, and, you know, go forward, back and forth. Okay, so that's just so you can kind of like see from a memory point of view, like the linked list. And I think that kind of gets one more piece I want to talk about is like generally like how classes. Now classes aren't in C. Classes don't exist in C. Classes exist only in C++. That was sort of the big thing with C++. Although C does have structs, which are basically like kind of like classes just without functions. So let's see here. Let's just free up all our memory. So I'm just invoking the free function and freeing up the memory. Again, you don't have to do this in JavaScript, Python, or Ruby because they have what's called a garbage collector. So the minute that you no longer need the memory, it just empties it out for you. Okay, but let's pretend that I have a class, okay? And this class, we have a couple different properties. We're going to have like a name, and we're going to allocate 10 up to 10 characters for a name. So, you know, this is, so that's 6, 1 2 3 4 5 6 name. So then we allocated the space for the 10 spots of memory for a name. Then maybe there's something that kind of like designates the end of that property. And then we also say, hey, we want allocate the space for a 2-digit number for age. Okay, I'll say like 35. And that's two numbers, 35. Okay. Well, think about that. Well, we'll just do it that way. It's technically it'll be a little bit different, but okay. So in that case, every time I use this class, and then again, there's something that marks sort of the end of this structure. So every time I create a new class, it's actually going to allocate enough memory for all the properties that I've defined in this class. So let's say this is the person class. Again, the person has a name and an age. So if I were to create a new person, it would then allocate memory for that new person. Then I can allocate memory for a new person. But see, it's all right next to each other, making it pretty quickly. If I need to get to this person's name and then get to this person's age, they're right physically next to each other in memory, so it's pretty easy to get there. And at least in JavaScript, this is technically what's happening when you use objects. Everything in JavaScript is an object, even an array. So technically, when you create an array, it's creating an object that's been that works like an array. There's actually a built-in object called array in JavaScript that's really a class. And when you create just like a single object, really what it's doing is creating a class. It's basically creating a quick class and then using that class. So then what happens is really just taking a block of memory based on the object you just defined and then injecting all the information in there. And that allows it to kind of be dynamic. Now exactly how it does its like push and pull operations, again, I'm not that deep or knowledgeable about necessarily how everything is implemented in JavaScript. And when you say JavaScript, that's a loaded term because there's multiple JavaScript engines. Like I think Firefox, I always forget, there's like I think 2 engines now. There used to be 3. I think V8's the big one. V8's the one created by Google. That's a JavaScript engine, meaning it's a piece of software that takes JavaScript code and does all the stuff underneath. So you could actually have multiple JavaScript engines, and what the JavaScript is doing performance-wise under the hood, it could be different. Okay? So you got to be careful. There's the language syntax, which really, that's just the syntax, has nothing to do with necessarily what's going on in the memory. And then there's the way it's implemented in the memory. But the idea here is to help you kind of think through sort of what's going on when you have implementation. Okay, and this is why everything, and here's the thing, like when I take a look at the data number 4, okay, that's an actual piece of data that's stored in memory. But if I take a look at an array, 4, 5, 6, this array in itself is not a value. It's a sequence of spots in memory. This is why in languages, arrays, objects, all these kind of types of data structures, they're always technically pointers. So if you'll notice, like, let's say in JavaScript, you can pass a number to a function, and if you alter that number, it doesn't alter the original variable you passed in. But if you were to pass in an array or an object and then alter it inside of a function, you actually do alter the array or the object, because these are always passed by reference, because there isn't an actual, like, there is no thing that's the actual array. The array, the object, is really just a block of memory that has several pieces of information inside of it. So what you're really passing to the function is the address. You're passing a pointer, meaning you're saying, hey, look, here's the block. Here's the block with all the data. So then when you're manipulating that, you are actually manipulating the data that's in memory. You're not making a copy of it. Okay, this is why typically primitives, numbers, booleans, and booleans are really just zeros and ones. But booleans, strings, and strings are just a single Unicode character. Well, a character is a single Unicode character, and then a string is just an array of Unicode characters. So technically these are each individual a char, C-H-A-R, like a character. And then this is really just an array of characters. Okay, this is why you can actually use like array functions in JavaScript on a string, because at the end of the day, a string is really just an array of letters. Okay, and letters are just a character. And then every character in Unicode encoding is just numerically defined. And if you haven't watched the video, The Unicode Miracle, check it out on YouTube. It's a really good explanation of what that means when I say like Unicode types and how they refer to in a computer. It really, really, really is super cool. But yeah, so hopefully this helps you kind of imagine that, like, one, like, why memory matters, because again, there's a finite amount of memory that the computer has. So if I were to fill all this up, okay, the computer's not going to necessarily have memory to sort of work with to do its operations. And here I'm not even like making a distinguishing between the stack and the heap. That's a conversation for another day. Okay, but we're just going to say there's a finite amount of memory, and the less there is of it, the less room that the code has to sort of continue doing continued operations. So then it starts slowing down because it's waiting for other memory to free up to finish whatever it's doing. And then on top of it, so there's a lot of things that sort of affect performance. There's your usage of memory. There's the speed of the processor of the computer that's running the operations. Okay, a faster processor can process more stuff. More memory means you can actually have sort of more information easily accessible. Okay, because then what happens if I fill this up, the computer may end up having to use some of your hard drive as memory, but your hard drive isn't something that it can access very quickly. Because, I mean, nowadays you have solid state hard drives, which are just big giant like chips. But a lot of traditional hard drives are really literally spinning disks. It's like a tape that's spinning in circles. So you have to wait for like it to spin in the right spot to have access to that particular piece of information, which is not as fast as like your sticks of RAM that are in your machine, which are more like this, where it's just like literally like a grid of data that it can just jump around from, instead of trying to catch information from a spinning disk. Like there's physical limitations here, and good memory management allows you to minimize that. And this is why, like, when you're creating a program that needs a lot of speed, think about video games, think about operating systems. And when I say video games, I mean like think of like AAA titles that use a lot of 3D rendering, real time, and there's a lot of stuff going on. Those are going to need very efficient memory management, which is why they're going to use languages like C, C++, Go, Rust, which are built to be faster because they're giving you a much more lower level API, which means you have to do more yourself, okay? Or working with arrays is going to be a lot harder. But when you're doing things that are not super memory intensive, like a very basic API, scripting, things like that, languages like Python, JavaScript, Ruby are beautiful because they allow you to just create what you need really quickly. Speed isn't as much an issue because the scripts are so small. I mean, what you're doing with them isn't so small in scope most of the time that you're not going to really notice a speed issue. But nowadays, you're starting to see like the web become sort of development entirely. Everything is a web thing. So web servers are doing more work than ever before. A lot of these things are starting to bleed into the complexity, and this is why like languages like Go and Rust are starting to become popular because people need something, but C and C++ can be pretty hard. And plus, like, their workflow can be a little tricky because C and C++, kind of like how I said there was multiple JavaScript engines. So there's multiple ways that JavaScript can work. C and C++ have lots of different implementations. So there's a lot of different compilers, a lot of different compile targets, and each of them sort of change how C and C++ work under the hood. So there really isn't sort of like this uniform package manager workflow, because it didn't evolve. It was before really you would think about those things. It was created. So and there really won't be because it's such a weird, diverse language. So Go and Rust offer a language that gives you sort of a more low-level API like C and C++, yet how you work with it's much more uniform. Okay, you're working with Rust, you're using Cargo as your package manager. If you're working with Go, you're using Go modules, but you can still compile to all the same places, and all that stuff was kind of thought through ahead of time in making those languages because they were made with hindsight available. Hindsight of like, oh, what would have been nice if we had to redo C and C++, what we would have done differently. But hopefully with this. So overall, hopefully, I threw a lot of information at you, but hopefully on top of this, it helps you appreciate like why data structures matter. Because again, if you're working with a language like C or C++, there's a lot of aspects of data structures you just sometimes have to just recreate yourself. And because you're working so much more granularly with the memory, understanding how these data structures work inside the memory help you kind of think through sort of like, how can I set up my program for the best performance, because I know, okay, this is going to behave this way for the memory. Again, if you're doing, basic web servers and APIs and light scripting here and there, probably this won't necessarily matter as much day to day. But as applications grow, as you start worrying about scaling and performance, these things do become matter, and then this knowledge can be the difference between from being in one position towards a higher level position where you can make more money. So, yeah, my name is Alex Merced from alexmercedcoder.com. Like the video, subscribe to the channel. Make sure to head over to devnursery.com and join the Slack and Discord community. Have a great day and enjoy.